All right, can you hear me? Yes. I think we're going to start. So today we are very happy to welcome back Professor Jesse Thaler. Jesse was an undergraduate here at Brown. He wrote a thesis with Professor Antal Javicki, for which he was an APS APCO Award finalist. Then Jesse moved to Harvard for his PhD under the supervision of Professor Arkani Hamed, and he joined the faculty at MIT in 2010. Professor Thaler has made several important contributions to particle phenomenology, including in jet physics and searches for dark matter. He won numerous awards. I have a huge list: DOE Early Career Award, White House Presidential Early Career Award, Sloan Fellowship, several MIT awards for teaching and advising, and last year he was also named an APS Fellow and Simons Investigator. Now, in recent years, he has been at the forefront of the movement to bring techniques from machine learning to address outstanding questions in fundamental physics. And he is currently a director of NSF Institute for Artificial Intelligence and Fundamental Interactions. So there's Professor Thaler.
Right. Thank you so much. It's a pleasure to be back. I was class of '02, so this has been 20 years, and I was back for my reunion, got a chance to see the new Brown Theoretical Physics Center. And what I remember from my time as an undergraduate was sitting where you were. There was the coffee, there was the cookies, and I remember this crazy long-haired guy who came in to give a colloquium with flimsies, and that person ended up being my PhD supervisor, Nima Arkani Hamed. And so it might be that in this room, you might meet someone, me or someone else, who could end up being someone who has an influence on your life. And folks here at Brown have been extremely influential, and so I really credit the faculty here, some of them sitting in the front row, for educating me during my formative years, and it's really a pleasure to count them among my colleagues. Now, I've been doing something crazy for the past 5 years, at least crazy from my previous work. 5 years ago, I was making fun of my friends who were doing all this deep learning things. And then now I find myself as the director of an NSF-funded Artificial Intelligence Institute. And so I want to tell you a little bit about particle physics, how it looks like through this lens of machine learning. First, I'm required to actually advertise. So this is an unskippable ad where this is our NSF Institute. Our logo here can either be read as a AI or an FI for Artificial Intelligence and Fundamental Interactions. It's a joint venture in the Boston area between MIT, Harvard, Northeastern, and Tufts. And what we're trying to do is bring together communities, physics theory, physics experiment, and foundational AI, to advance physics knowledge from the smallest building blocks of nature, that is, particle physics, to the largest structures in the universe, cosmology, as well as galvanize AI research innovation. And if you want to do this in slogan form, you can think about this as trying to infuse physics intelligence, whatever that means, into artificial intelligence. Machine learning that incorporates first principles, best practices, domain knowledge from fundamental physics. So I could give you a whole colloquium about that. But I feel actually like what I should do is apologize for myself, or at least explain to myself where I got to. And so this is going to be a semi-historical view going back 5 years-ish, when 2 graduate students, Patrick Comiskey and Eric Metodiev, came into my office showing me a paper that they'd written with their master's supervisor, Matt Schwartz at Harvard, about weak supervision for the strong force. Okay? Actually, that was not their paper. The story I'm going to tell is weak supervision for the strong force. They were doing strong supervision for the strong force. So actually, just by show of hands, if I say the words weak supervision and strong supervision, by show of hands, how many people know the difference between those two? Okay. And if I say weak force versus strong force, how many people know the difference between those two? Okay, good. So I'll have to explain what I mean by weak supervision. Patrick and Eric come to my office at MIT, and they say, ooh, there's this really cool convolutional neural network that we've done that can tell the difference between quark jets and gluon jets. And please have us as your advisor. And I basically just, I don't want to say yell, I was kinder than that, but I told them all the reasons why their paper didn't make any sense. And in particular, I asked a question that I was obsessed about at the time. What do you mean by quarks and gluons? And I meant this in a very technical sense that I want to try to explain today. So I'm going to spend a third of the talk just trying to explain this question. Quarks and gluons are the fundamental ingredients that describe the strong force. You would think, as someone who's worked on quantum field theory and has thought about the strong force, that I would know what quarks and gluons are, but I do not. And I want to try to explain why I didn't know and why I was skeptical of machine learning strategies to try to answer questions like this. And then, 5 years later, I finally know the answer. And this plot that includes Patrick as one of the collaborators, then Serhii Kriyan, who was an undergraduate at MIT, as well as a huge number of other people contributing to this body of effort. We made this plot, and this plot, I don't know whether you're impressed by it. Certainly this does not look like a machine learning plot. Right? When you think about machine learning plots, you imagine typing something into DALL-E and generating some psychedelic image or something like that. You think about self-driving cars. You think about robot apocalypse. You don't think about writing down a curve that describes the scaling dimension of quark and gluon degrees of freedom in the strong force. But this plot is infused with machine learning in a way, but also infused with quantum field theory in a way that I'm going to try to explain today. And requires things for machine learning like weak supervision, topic modeling, permutation variant networks, simulation-based inference, optimal transport. But it also gets access to a question that I had 5 years ago, in fact, longer than that machine learning gave me a way to answer a question that I don't know how to answer any other strategy other than the one that I'm going to show today. Okay. So I'm going to try to walk you through the story, and I'm going to walk it through you roughly chronologically. So try to explain where I was back in 2017 when I was making friends of my friends who were thinking about machine learning. What changed my mind around 2018? And then I'm going to run out of time. And so to explain that plot before, I'm going to rush through 2019, 2020, 2021, 2022. There was a pandemic then, nothing really interesting happened, right? But revisiting the strong force using this. This by itself is probably like 2 or 3 talks, so I'll just give you kind of rapid fire sense. But what I want you to come away from this colloquium is thinking about how machine learning strategies or machine learning reasoning might be relevant for your field. What are questions that you're skeptical that a machine could ever answer? And then try to phrase it in a language that maybe the machine could actually give you insights that you couldn't get through the way that you're approaching your research right now. Certainly that's what happened to me, and I went from a machine learning skeptic to now director of an AI institute, and now, as you see, a machine learning evangelist. Okay, so first I need to remind you about what quarks and gluons are, and remind you about the standard model of particle physics. So this is a kind of a particle physics 101. We usually draw this kind of pie chart representing the fundamental degrees of freedom at the shortest distance scales of nature. In orange are the quark degrees of freedom. In green are the lepton degrees of freedom. The force carrier is in blue, and the Higgs boson, the kind of cornerstone or the centerpiece of the standard model, shown in purple. And if you don't know anything about particle physics, you might imagine that you actually see these degrees of freedom, that we've done experimentation to actually see each of these degrees of freedom, and that's very far from the truth. Of this pie chart, only 3 of them, roughly speaking, photons, electrons, and muons, basically the ones that only carry electromagnetic interactions, only those are ones that we actually can hold in our hands, if you'd like, that actually hit our detector. Quarks and gluons, they can find by the strong interaction. And so I never see quarks and gluons in a liberated state. Instead, they make composite states that have funny names like pions and kaons. The most famous ones, the ones that form nuclear structure, are protons and neutrons. And everything else you have to infer, for example, by its decay. So top quarks, Higgs bosons, W and Z bosons, those decay very quickly. Taus live a little bit longer, but still you can only infer their presence by their decay products. Neutrinos, just when you make them, they sail right through your detector, so you infer them from their absence. But inference is a huge part of what we have to do in particle physics, and machine learning is very good at inference. So going from these elementary and composite degrees of freedom to reconstructing the standard model, or what might go beyond that, is something where machine learning has played an incredibly important role in our field. And it's worse than this. I'm a theoretical physicist, but I care about the way that one interfaces with data. So you actually don't see photons, electrons, muons. What you see are hits in your tracker, or deposits in your electromagnetic or hadronic calorimetry, or you have specialized detectors that see muons. And every 25 nanoseconds at the Large Hadron Collider, you get these sprays of radiation that you have to figure out what's going on. You have to infer the underlying physical processes in terms of standard model degrees of freedom. My specialty are these jets, these things that are represented by these orange cones. Of course, you don't actually get these orange cones from nature. This is our reconstruction of what's going on. These jets are proxies for quarks and gluons. Roughly speaking, when you see this collimated spray of radiation, you should be thinking about that starting off that spray was a short-distance quark or gluon that immediately turned into this complicated, strongly coupled mess as it flies out. And this is like kind of like relativistic beaming that causes you to have this collimated radiation pattern. And somehow from this debris that's happening at a rate of 40 megahertz, or every 25 nanoseconds, we're supposed to understand the fundamental structure of the universe. And so maybe with a problem that complicated, it's maybe not so surprising that so many people are enthusiastic about machine learning for this type of challenge. Let me show the same story in movie form. So this dot here represents a proton bunch at the Large Hadron Collider. Each dot there is really 10 to the 11 protons, so that's roughly the same number of stars in the Milky Way. So if you take the Milky Way and Andromeda, they're eventually going to collide into each other, and the number of collisions is roughly the number of collisions you get each time these things interact. This is getting injected into the Large Hadron Collider. There's 4 detectors, CMS, ELISE, ATLAS, and LHCb. Brown is involved in the CMS experiment, but this is an outreach video from ATLAS. They put the graffiti version of the standard model on the wall. There's these superconducting tubes that are bending the protons around. We're going to cross the Swiss-French border and go inside the superconducting tubes, take a cartoon version of this complicated, strongly coupled mess that corresponds to a proton. And a proton is going to be fired at another bunch of protons into the center of, in this case, the ATLAS detector. And there's a crucial moment of time where everything is perturbative. I can do my favorite quantum field theory calculations in terms of quarks and gluon degrees of freedom. Things are well behaved. I think I understand what the definition of a quark or a gluon is. Unfortunately, this instant of time is not one that we can actually resolve. We don't get to see the degrees of freedom underlying this process. Rather, what we see is the collimated sprays of particles coming out. These white lines are charged particles. These green and yellow hits are electromagnetic calorimeter deposits. And then rotating into view are these reconstructions of these cones of radiation. And somehow, we're supposed to take this complicated radiation pattern and decide, oh yes, I had proton-proton scattering that made, let's say, one quark jet and one gluon jet. Somehow I'm supposed to infer that from this debris. And then from that inference, I'm supposed to do precision calculations to ask, okay, is the rate at which I made these in agreement with what my theory predicts, or is there some deviation that might signal some sign of new physics? Again, a very challenging inference problem. And I've made a career thinking a lot about jets. And so for me, this is like looking at old family photos, like these are my friends. So I don't know whether you find these beautiful. I find these really beautiful, different ways of representing the spray of radiation. Again, every 25 nanoseconds, one of these things are happening. I find this beautiful and amazing. I have colleagues who absolutely hate hadrons, and so they think this is all disgusting. They only want to look at nice, clean photons, electrons, and muons. For me, again, these are my friends. What actually caused this? Is this... I mean, I happen to be in this field, so I can tell you, oh, that's that spray of radiation, these yellow lines, that probably came from a top quark. You're like, well, Jesse, how did you do that? Well, I used my eyeball. I knew my domain knowledge. I'm doing what this little neural network is doing some work. But some of these other radiation patterns, I'm not sure I even understand what's going on here. How would I teach a machine how to do it? And maybe more fundamentally, what do I mean by a quark jet versus a gluon jet? So now let's go back in time to 2017. In 2017, I got a team of 10 people together to try to hash out in the Swiss Alps, what do we mean by a quark jet versus a gluon jet? Why is it a problem? Why is it a challenge? So quarks and gluons are degrees of freedom of the strong nuclear force. The strong nuclear force is described by an SU3 gauge theory. Different particles come in different representations of that gauge theory. Quarks correspond to the color triplet mode, and gluons correspond to the color octet mode. But because of the confining nature of the strong force, jet constituents are color singlet hadrons. Color information, the thing that defines the chromo in quantum chromodynamics, is gone. You cannot unambiguously say whether you made a quark or a gluon, because just by the conservation laws, the things that you're seeing have different representations than the fundamental degree of freedom. We made this chart about like ill-defined to well-defined, what sometimes people think we mean, what we actually mean. And the most rigorous definition, this is back in 2017. By the way, this is an old problem going back to at least the 1980s, if not before. And I'll just read this out. I'll read it twice. We decided that the best definition of a quark or a gluon is a phase space region as defined by an unambiguous fiducial cross-section measurement that yields an enriched sample of quarks as interpreted by some suitable though fundamentally ambiguous criterion. Let me say it one more time, because it just really rolls off the tongue. A phase space region as defined by an unambiguous hadronic fiducial cross-section measurement that yields an enriched sample of quarks as interpreted by suitable though fundamentally ambiguous criterion. I did not get into theoretical physics to write sentences like that. I wanted to understand like the fundamental nature of the universe. And this is the fundamental definition of what a quark or a gluon is. We were correct back in 2017, and machine learning actually provided exactly that for us. This is what we wanted. This is the only thing that we thought would make sense. And indeed, machine learning provides that. And it's taken me a while to explain where I get that. Let me just say it one more time. I really want you to understand that this is, like, again, people have been talking about it since the 80s, and somehow we have this idea of, like, old ideas are not interesting ideas. In many cases, old ideas are really ripe for someone to come in and really attack it in new ways. And a variety of my colleagues have been revisiting the strong force through new lenses, like lenses through holography, for example, or lenses through conformal field theory have been really inspirational. But again, for this talk, let me just emphasize the problem. I slam together my protons like I had in the movie. Sometimes I make quarks and gluons. Quarks and gluons themselves, perturbatively, behave just like electromagnetic charges in the sense that when I have a quark, it radiates gluons. In the same way that I have an electron and I accelerate it, it radiates photons. A little differently is that gluons themselves radiate, so photons don't radiate more photons, but gluons do radiate more photons. And the way that this radiation is dictated is by a famous formula called the Altorelli-Parisi splitting kernel, which is going to appear multiple times in this talk as I try to unpack this formula in the language of machine learning. It's a core prediction of QCD. We believe it to be true. And it says that the amount of radiation that you get is proportional to the coupling constant, alpha S. That's the equivalent of the electromagnetic coupling constant in QED. The charge, in this case, the charge of a quark has this funny 4/3 number, and the gluon charge is 3. A collinear radiation singularity, so this basically says that radiation wants to go parallel to the direction of transport. We know this from electromagnetic radiation that tends to track the direction that charges go. And then a soft singularity that says that the amount of energy that the gluon takes tends to be small. These are called the soft and collinear divergences. They're universal across gauge theories. Fundamentally, quarks and gluons are distinguished by their color charge. If we could go in and zoom in and look at these emissions, we would just be able to read off what's the charge. Just like we don't, it's not ambiguous when you look at a charged object and say how much charge does it have in coulombs. We should be able to read off this 4/3 and this 3. But damn it, we can't because they confine into these pions and kaons by the strong force. It's even worse, they hit our detector. And maybe you're a clever theorist who says, oh, I know what I can do. I can use some of my knowledge about quantum field theory and try to sidestep all these complexities and introduce theory calculations in terms of an operator that actually tracks the flow of energy off to infinity. And there's a whole body of work that I'd be delighted to tell you about that's trying to sidestep these complications. But when you sidestep these complications, you end up coming up with a way of characterizing collider data that's robust to these complications, robust to hadronization, robust to detector effects, but sadly blind to this quark-gluon information that I want to get access to. This is the challenge. So if I'm going to tackle this with machine learning, what do I need? I need some insights. I also need some data. Machine learning is trying to learn from data or make decisions based on data. And remarkably, around the same time when I was wrestling with quark and gluon challenges, there was a monumental release of public data from the CMS experiment. That was one of the 4 collision points that I showed you along the ring. Not the one that I showed you the video of. The Atlas experiment refuses to release their data publicly, which is a fascinating story that I'd be happy to go into, and how many friendships that I've broken because of complaining to my Atlas colleagues. I'm still friendly with my CMS friends. And we were able to study the part of the Altorelli-Parisi splitting kernel that didn't care about quarks and gluons. And so I could give a whole talk about this. This is a color-blind test of QCD using public data from the CMS experiment. To my knowledge, the first ever analysis using this public LHC data. And the details of this thing don't really matter. But in this Altorelli-Parisi splitting kernel, this dz over z, we found a strategy to actually see that 1 over z-like behavior in data for the first time. This is something that's been known to the 1970s, but no one processed the data in a way that exposed this term so clearly as we were able to do. Unfortunately, this thing is insensitive to the quark-gluon composition, and we want to be able to do the opposite. And again, at this time period, 2017, when these papers came out, I thought it was impossible. Okay. Any questions about the question? You can question why I'm so obsessed with it. It seems like a big to-do about just this little thing about the definition of what we're doing when we're doing quantum field theory calculations, but yeah, for me it was important to understand. So just to summarize what I've told you right now, jets are manifestations of quarks and gluons, but there's no unambiguous way to tell a quark jet from a gluon jet, and that's going to persist in the rest of this talk. So now I need to explain to you why I have this cute koala reading a book, not the type of graphic you typically expect to see at a physics colloquium. So where's that coming from? And this is now introducing this field of weak supervision. I'll try to explain the difference between weak supervision and strong supervision. So other fields of science have already known about this challenge of how do you disambiguate different processes, different physical processes. So here's an example from cosmology. When we see this beautiful baby picture, the leftover remnants from the Big Bang, and we say, oh yes, we've extracted the cosmic microwave background, we're hiding what's actually going on in terms of the data analysis, which for me is actually quite fascinating. You measure the sky in different frequency bands, and you get different sky maps. Those different sky maps are sensitive to different features. So there's, of course, the CMB that we want, but then there's all this contamination. Detector noise, synchrotron, galaxy effects, thermal noise, thermal and Doppler behaviors of clusters, things that if you asked me what they actually are, I couldn't actually tell you since I'm not a cosmologist. But we have some number of sources, some number of measurements, and if you assert that this linear combination and this linear combination are related by some kind of, let's say, unitary transformation or orthogonal transformation, then it's just a linear algebra problem to say I measure all these frequency bands, assign them to these categories in some way, and this is known as blind source separation, where you're able to infer what the underlying distributions are from certain assumptions about how they are mixed together. So cosmology does this already, and this is something that we can actually apply to quark and gluons. I'm going to explain this in more detail in a moment. Could we do this blind source separation for quark and gluon jets? And the analog in the cosmology case is that if I look at a PERT in the sky and I see a photon, I cannot tell you whether that photon came from dust or the CMB. But ensemble-wise, I can do this kind of rediagonalization and tell you at least kind of an expectation whether that photon was from one source or another. So you cannot unambiguously label individual jets. But nevertheless, you can extract the distributions of quarks and gluons from hadron-level measurements. From measurements on color singlets, you can get access to these color triplet and color octet information. And the reason why I'm showing this as the stack of documents is that we learned about this work. This is with my former students, Patrick Kaminsky and Eric Metodiev. We learned about this work in the context of natural language processing, where this is known as topic modeling. So what you can imagine is that the way that your textbook is written is you have a bunch of buckets. Let's say we have a math bucket and a physics bucket and maybe like a poetry bucket. And then you pick words randomly from those buckets in some proportion, and that's the way you're going to write your textbook. And then somehow, from reading the document and reading a bunch of documents drawn from the same buckets, you actually invert it and then say, oh yes, this is the bucket corresponding to mathematics. This is the bucket of words corresponding to physics. This is the bucket of words corresponding to poetry. And let me try to give you this as an example of like why even in principle this might be doable. Let's say I say the word energy. If I say the word energy, you could say, that could be a physics word. It could also be like a climate science word. If I say the word energy conservation means something very different to a physicist than it would for someone running a power company. But if I say the word Noether's theorem, like that, you're like, oh yes, that you must be a physicist. Or if I say the word Kyoto Protocol, it's like, oh yes, you must be someone who's worrying about clean energy and climate science. And there's these key features of words, just like there's key features of jets that you can use to actually disentangle the categories. You can't disentangle any individual jet from another one, but you can use this information about what's called as anchor words, or in our case, it's anchor histogram bins, to invert this process and come up with the category. So again, here I'm imagining a document. Sometimes I'm writing quark, sometimes I'm writing gluon. They're drawn from the quark and gluon buckets. I make this histogram. And as long as I can make enough histograms with different mixtures, I can actually invert this to figure out the underlying quark and gluon distributions. What does this require? Anytime you have machine learning, there's always a requirement or assumption behind the scenes. And in this case, the assumption is that you can make samples of jets that are mixtures of quarks and gluons. Just like in this document case, you can make documents by randomly sampling words from various buckets. So I say that my mixed sample is some fraction of quarks and some fraction of gluons Each quark could look different. Each gluon could look different. In fact, there's certain cases where you can't unambiguously say, hey, was this a quark or was this a gluon? And then, if you can identify some region of phase space, so it turns out that if you take one of these particle physics detectors and you look at jets that primarily go in what we call the forward region, these ones tend to have a higher quark fraction than ones in the central region. And with this assumption that I have two buckets of mixed stuff that I can do this inversion, this is a non-trivial assumption, assumes that these mixtures have unbiased properties. But with this, you just go to your statistician friends and say, OK, please invert this for me. Please define quark and gluons from this fundamental equation. So this is either obvious and trivial or magical. And how the heck is this possible? Now I think it's obvious and trivial. When I first saw this, I was perplexed. So this is crazy. Wait, so you're telling me I take a mixture of jets here. I don't know whether they're quark and gluons, some mixture. Take another mixture, some mixture of quark and gluons, I don't know, some mixture. And you're telling me that from this, I can infer the properties of quarks and gluons? Yes, there's an operational definition, a thing that I can do. I basically take sample A, subtract off sample B by some coefficient, and push that coefficient to the extreme where something bad happens to the probability goes negative. And right before it goes negative, once it hits 0, you stop there. You have a valid probability distribution that defines what's known as a mutually irreducible distribution. You do that for A minus B, that gives you quark. You give it for B minus A, and that gives you gluon. Choosing this kappa value as big as possible yields mutually irreducible distributions. And I go from saying, what the heck are quarks and gluons, to having actual formulas that say, here's what you would do both in a first principles theory calculation on your experimental data to get you the most mutually irreducible categories, which I need to put in quotes because, okay, I am putting my own kind of interpretation on it that I think that these are correlated with quarks and gluons in some way. But really, all this is a data manipulation strategy to basically orthogonalize my observables. And this has been done. When we first put this out, we read this paper from our statistician friends, came out in 2016. We're like, oh, let's leverage it. We did it in 2018. And then the Atlas experiment, actually in 2019, actually did this. Region A forward, region B central. These histograms look nearly identical, but they're just different enough that you can split things apart and actually identify topic 1 and topic 2, able to extract quarks and gluons from data. No assumptions, no simulation needed, purely in data. People complain sometimes about machine learning that it requires knowledge of the problem you're trying to solve ahead of time before you can solve it. In this case, we knew the requirements, we knew the assumptions, but we're able to do this without any reference to simulation. Of course, then you can compare to simulation and see whether what you see in simulation matches what you see in the data manipulation. But these error bars here on the data are just coming from a data science manipulation, no theory input needed. Okay, great, but wait, you just did this with histograms. Don't jet topics depend on the choice of jet features? Aren't you still underlying, you're making some assumption about what you're going to measure about your jet? So it seems very circular. For example, I could just decide to measure jet, do you exist? For quark jets, they exist. Gluon jets, they exist. If I try to diagonalize, I learn nothing. And I know that they're different, right? But that's insufficient information to do things. And so that's where you get this koala holding a book. So the book is because of this topic modeling technique. And this cute koala is because we introduced a technique to find maximal separability using a technique called weak supervision. And we called this method of weak supervision classification without labels, which maybe if you read that is like koala. It was not one of my finer moments in terms of coming up with acronyms. I have a pretty good track record with acronyms. There's been various experiments, including an experiment called Abracadabra, which is, to my knowledge, the longest legitimate acronym in scientific fields. This is a not so legitimate, but still very cute acronym. And so now I want to introduce you just one more kind of machine learning thing. So this machine learning thing I told you before is just fundamental statistics, topic modeling, the ability to separate out pure categories. But now I want to separate pure categories where I don't have to make any choices about what jet features I use. Rather, I let a machine learning algorithm choose what jet features to use. So if I were doing strong supervision, this is the thing that you should be very skeptical about. If someone says I use strong supervision to train my neural network, you should say, ooh, that requires that you actually have examples that someone has appropriately labeled for you of what you're trying to accomplish. So here we're going to do binary classification, signal versus background, quark versus gluon, cat versus dog, whatever your favorite thing is. And if you had pure, perfectly labeled examples, assuming you had pure, perfect knowledge, which we never do, then what you would do is you would say, okay, take your signal, inject it into your black box classifier, take background, inject into your black box classifier, minimize the so-called mean squared error or some other machine learning loss. If you minimize that loss, then you get this particular classifier, H. And this classifier H, if it's optimal, then it interpolates between 0 and 1 in such a way that when H says 1, it's perfectly confident you have signal. When H says 0, it's perfectly confident that it's background. So if I'm in a region of phase space here, for example, where there's absolutely no signal, only background, then I get 0. If I'm in a region of phase space where there's absolutely no background, then I get 1. And this is the best you can do. This is the best you can do for separation. And so every time you see, like on whatever your favorite machine learning application, someone shows you like a self-driving car that says, that's a stop sign, that's a pedestrian, that's a car, that's a tree. This is what it's doing. It's doing something like this, only instead of having just 2 categories, it has multi-category. And when it's confused, when it says, is that a tree or a stop sign, I'm not so sure, it nevertheless gives you an answer, and there's some chance that it's wrong, which is why self-driving cars are not roaming our streets at this moment, because of how you attack this challenge when there's actually ambiguous input. But this is the best you can do. This is strong supervision. I gave a talk this afternoon talking more about how you actually derive this in a Lagrangian formalism. That was a fun talk this afternoon. But this is very well known, and this assumes that you have all the information. If you don't have all the information, then what do? I can have weak supervision. This is what an example of this is this classification without labels, where all I have is these mixtures. I have these mixtures, a little bit of quark, a little bit of gluon. I don't even know what it's like. It's like you have 2 buckets of jelly beans, and some jerk took one handful and put in the other one, and the other one, and somehow you're supposed to do a chemical analysis to tell the difference between red and blue jelly beans, but you only have this mixture and this. How would you ever do this? And here's amazing thing. It's a 2-line proof, which I'm not going to show here, but it's a 2-line proof that shows you actually that with this weak information, I don't have full information. I just need to assume that I have mixtures. I don't even know what fraction of mixtures I have. The ideal mixed classifier, which is given by this formula here, is not the same as the ideal pure classifier. It's solving a different problem. But nevertheless, with 2 lines of algebra that I'm not showing, this mixed classifier is monotonically related to the pure classifier, which means that this weak supervision, even though I don't have full information, yields the same decision boundaries as strong supervision. That is, I can make a decision, is my jelly bean more blue-like versus red-like? I don't know whether it's pure blue or pure red, but I can say, is it more blue-like or red-like, because of this monotonicity relationship. And then if you take this is the koala part, and then have the koala reading the book, using this topic modeling that allows you to get full separation, then you end up with this well-read koala, where if you train a machine learning classifier to try to separate things, it can't do it. It can't do it because pure, it would go between 0 and 1. With mixed, there's a maximum amount of separability because there's this mixing. But fine, the endpoints of this actually tell you exactly how mixed they are. And then from this, you can now undo things and actually get your pure distributions. So we're using machine learning twice. We're using machine learning to define the way we want to separate things out, and then using machine learning another way to actually figure out the maximal amount of separability, which is quite remarkable. And it was like this body of work that really made me say, oh, wait, this machine learning thing, I didn't show you a picture of a neural network. I didn't show you, any psychedelic images. This is just science and basic statistical reasoning that made me very excited about this. So by assuming jet samples are mixtures of quarks and gluons, one can operationally define jet categories. And then if someone wants to ask me a tough question, you can say, well, what if I don't make that assumption? What if they're not really perfect mixtures? How do you deal with that type of systematic? And I'd be happy to discuss that in Q&A. Okay, so now I'm supposed to put this all together and tell you about revisiting the strong force. I'm starting this part of the talk in 2019. Again, I've been giving some version of this talk clearly over this time period, and the number of remote talks that I gave during the pandemic about this. And it feels like finally I've come to the crescendo where I can see everything all at once. But sadly, I don't have time to go into everything in detail, so I'm happy to say more in Q&A if people are interested. But this is going to be kind of lightning going through a huge number of innovations that happened between 2019 and now. So 2019, something very interesting happened. In January of 2019, so this is pre-pandemic, there was a workshop at the Aspen Center for Physics on theoretical physics for machine learning. And what I saw was a collision course. So one was a collision course in the meaning of like teaching people about our field. So I was going around, in fact, I gave a talk at Google trying to explain, protons collide, you make these jets and so on. But there was another meaning of collision course, a collision between fields, and realizing that actually the high energy physics community, both theoretical and experimental, and the mathematics, statistics, and computer science communities were actually coming into collision and thinking about some of the very same problems, albeit in very different languages. I feel like I've gained new insights into particle physics facilitated by advances in machine learning. And now, as I've had conversations with folks from the mathematics, statistics, and computer science communities, I felt like we've been able to teach them something that they wouldn't have known without some of the physics domain knowledge. And so this has been a really fruitful intersection. And so now I have to go into montage mode. Apologies that I have to go through this really, really quickly, but just to give you some flavor of what was happening. So I said I didn't show you any psychedelic images. Okay, I lied. Here's a psychedelic image. So 2019, the type of data sets that I showed you in particle physics, the machine learning computer science folks call point clouds. They think about points in 3 space. We think about particles with momenta, px, py, pz, so points in momentum space, but mathematically they're the same thing. We introduced a type of neural network called an energy flow network that is a set-based architecture with an interpretable latent space. How do I know that it's interpretable? Because I can make a picture of it. And remarkably, this tangled web of kind of rubber bands is actually very closely related in a way that I'd love to explain in Q&A if people want to know, to the collinear singularity structure of QCD. Basically, you have jets going into the page, and these little circles are trying to capture basically one unit of information content. And the fact you have these smaller rings near the center and larger rings near the outside is saying that it knows that the information content is logarithmically distributed in this variable. So the collinear singularity structure of QCD, again, from this ultra-early Parisi splitting kernel, is coming out as an output of a machine-learned trained classifier using this set-based approach. Also in 2019, we interfaced with people in computational geometry. There's a field that's known as optimal transport, which is basically a way of thinking about how do you optimally move stuff from one place to another. So anytime you order from Amazon and you want to say, okay, Amazon has its warehouses, it has the houses that it wants to deliver packages to, how do we minimize the transportation cost of getting the stuff from one place to another? And in fact, that they're using optimal transport, because sometimes Amazon will tell you, oh, just keep it. It's too expensive for you to send it back, just destroy it. And in fact, there's a particle physics analog of destroying energy in this case. And you can actually take 2 different collider jets, one in red, one in blue, figure out the optimal transportation plan. That gives you a distance. That distance can be used to triangulate a space. That triangulated space has an interesting geometry to it. Okay, hugely fun thing, 2019. That in 2020, we were able to take this CMS public data and try to actually visualize the space that was learned by this optimal transportation plan. So what we're seeing here is we're seeing 30,000 jets, but only 25 circles. These 30,000 jets are being represented by this gray blob. This is like a histogram or a density over those 30,000 jets, of which we can use, in this particular projection down to 2D is called a T-SNE projection. So that's another machine learning technique. The way we chose these circles, this is like choosing selected trees from the forest that are representative of their neighbors. This is called a K-medoid strategy. We can actually make these circles, their size tells you how many neighbors they have, and inside of them you can actually see these radiation patterns. And if you stare at this long enough, you can say, they go from blue to red. Okay, that's because in red to blue is the old way that I, as a domain expert, would have labeled my things. I would label things in one dimension, going from blue to red. The machine has learned a second dimension. What is that second dimension? Going from left to right, we go from 1 lobe of radiation to 2 lobes of radiation. Going from bottom to top, we have asymmetric lobes to symmetric lobes. And it has learned, actually, the opening angle and energy sharing coordinates of the QCD ultra-early Parisi splitting function. We didn't tell it this. We just said, hey, please do a TC projection of our optimal transported generated geometry. And it came back and said, hey, ultra-early Parisi. That's amazing. Then you say, wait, you have this space. You have a space triangulated by this optimal transport. And I tried to show it in 2D by doing this projection, but really this thing lives in some like higher dimensional space. Can I compute the can I compute the dimensionality of that higher dimensional space? And again, with this public data, we're able to compute a scale-dependent dimensionality. So this spiral here is an example of a data set that, depending on what scale you look at it, actually has different dimensionality. So if I zoom in really, really small, then all these data points are doing their social distancing, so it's zero-dimensional. As I increase the size of my ball, the number of neighbors doesn't change. That's zero-dimensional. When I zoom out further, I see that these points are arranged kind of in 2D, so that as I increase the size of my radius, my number of neighbors grows like the square of my radius. That means I'm two-dimensional. Zooming further out, I see that my number of neighbors scales linearly. That's one-dimensional. I zoom out further, and I see that I'm back down to having a zero-dimensional kind of dot. We can do exactly the same thing with our jet now, where we take those 30,000 jets that I showed you on the previous page, project into 2D, but now do this kind of scale-dependent analysis of it, where if I go to the energy scale where that jet was created, I get a zero-dimensional system. Why? Because I have just a single quark or gluon. And then as I zoom out, I see this more complicated radiation pattern developing, and actually it keeps growing and growing in complexity. This is basically a superfractal structure, that as I zoom in, I get more and more complexity, unlike a fractal where the complexity asymptotes to a certain value. Okay, this is like amazing. And then we say, oh, wait a second, does this actually have anything to do with QCD? And the answer is yes. This is actually the scaling behavior of QCD, and experts would actually recognize this as being a data science version of an anomalous dimension. Okay, but then I see this blue curve here. That's the actual kind of theory prediction. The yellow curve here is the detector distorted effects. And you say, oh, shoot, my detector is distorting the physics that I'm trying to understand. Maybe I need to correct my detector effects. And more machine learning comes in also in 2020. A multidimensional unbinned approach to do detector corrections by linear application of machine learning reweighting, where you can do some clever manipulation, blah, blah, blah. We call this thing omnifold. Omnifold has actually been applied to some collider data. Okay, we're ready to go, and we're ready to like really deploy this, do all the maximum analysis, and then the COVID happened. And so then I went around starting an AI institute, giving talks, but never really having the punchline to this story. Okay. But again, I went through this way too fast. But these are all machine learning-based things, right? It's about classification. It's about computational geometry. It's about data science analysis strategies to estimate properties of data sets. It's about trying to deal with experimental realities. Okay, all threads that are in the machine learning world that we'd like to put together. And so now, in 2021, the launch of our Physics AI Institute, where we really had an opportunity to bring together experts from physics theory, physics experiment, and AI foundational work. And I saw this as an opportunity to finally kind of try to put the AI back in ultra-early freezing. So I already showed you how the scaling behavior, these singularity structures, what you see, what can we not get? I want that color factor. I want to be able to separate quarks from gluons. Also, by the way, if you invite me to a colloquium in 10 years from now, I'll try to figure out how do you extract the strong coupling constant from this. And maybe 50 years from now, when I'm really senile, I'll try to extract pi from my collider data. That's when you should push me aside. Okay. But right now we want to separate quarks from gluons. Okay, so what do we have? I'm exhausted, I'm sweating. I want to get your questions. So what do we have now? In 2022, finally putting all the pieces together. So first, names of the folks, so Patrick Kaminsky, Sari Kriyan, Eric Metodiev, Radha Masandria, Preksha Nayak, Anders Andresen, Ben Nachman. Okay, all these people contributing on various aspects of this project. The plot that I showed was made just by these two folks, but benefiting from this experience. Also benefiting from the CMS experiment, who made their data public. Oh, benefiting from the entire AI community, who made a lot of this code available in terms of easily downloadable and runnable packages. So the story I've told you thus far is we have quark and gluon jets from the strong force. Confronted with public collider data. Machine learning is a data-driven field. We need that data. Unfolded for detector effects using this particular machine learning strategy called omnifold. Disentangled using weak supervision on set-based classifiers with topic modeling. So that's the koala, the psychedelic image, and the documents. And then finally triangulated using this optimal transport technique. And in the past, I've given like separate 1-hour talks about each of these pictures. Oh, and by the way, there's all this technical complications, which you can ask me about, some technical details about actually how you do this. But at some level, once you've extracted the fraction of quarks in some sample, the rest is just linear algebra. And so basically, we're just trying to get two numbers, the quark fraction in one sample, the quark fraction in another sample. Again, these two mixtures. And then from that, I can disentangle and put all these things together. So again, I'm happy to tell you more about what these plots mean if you want. And this is the dimensionality of quark and gluon jets. On this side is all, well, the solid lines are all data. The dashed lines is a theory prediction from a particular simulation tool. And this equation is what we can get from a first principles QCD calculation computed to lowest order. So again, what are we seeing? We're seeing that at scales corresponding to the scale with this jet was produced, we have 0 dimensionality. As I go down, we see that that dimensionality increases. But the amount that it increases depends on whether I'm looking at quarks or gluons. Now, this is kind of fun. When you're computing this dimensionality, you have to decide what points are you going to be starting your dimensionality with, and then what points are you going to be searching for friends from. So what gluon means is that I take all my gluons, ask how close are they to other gluons, how many neighbors do I have as a function of scale, and I use that to define my dimensionality. Quark is done in the same way. Quarks, how many quark friends does it have? And then quark gluon is saying, I have quarks, and I want to know how close are my gluon friends to me. And the first principle calculation that you can do has this alpha s and pi, logarithms because quantum field theory gives you logarithms. And then the color, these curves, the way that it goes up is a sum of the color factors involved. And so we get the color factors of QCD. And I remember when Patrick first made this plot, I was like, oh, that's nice. You see gluon, quark, quark. And I said, this formula, let's just check. It looks nice, but let's just check. And when he showed me this plot, again, maybe this is only something that someone who's been spending 5, maybe 10 years of my life thinking about quark-gluon discrimination would only love. This is taking the ratios of those various curves. And what you see here is if I take the ratio of the glue over the quark, you get exactly this 9/4, which is the relationship of 3/4. Again, there's no simulation here. This is fully data-driven extraction of the color ratio. This one is actually coming from just a consistency check. It works out. And then what's really satisfying is that in solid is the result from the data. That's the thing you should be comparing to the horizontal line. And it works pretty well. That calculation that I showed you is a very low-order calculation. It has some corrections to it that we have not gotten around to compute yet, but it works pretty well. If I took my simulation tool, the simulation tool that back in 2017, remember I got these people together to argue in the Swiss Alps about what one should do, and it's like, oh, we don't understand quarks versus gluons? Well, we really don't understand quarks versus gluons. This dashed line here is a simulation tool that actually models this behavior incorrectly. Actually doesn't have really the right quark and gluon properties, and we kind of understand even what's wrong in that code. So if we were to trust the code and do strong supervision on it, we would have come with the wrong conclusion. But because we used all these weakly supervised methods, we were able to gain insights into the strong force that I don't know how to gain using, again, traditional techniques. So we gain new insights into the strong force by fusing advances in machine learning with insights from quantum field theory. So that's the end of the story. Okay. A lot of stuff that I swept under the rug. Also a lot of backup slides if you want to know more. But we start off with this quark-gluon conundrum. And what I like about this example of quark and gluon jets is it offers an extreme example where fully supervised learning or strong supervision is fundamentally ambiguous. And here, this is a case where I could legitimately stand up and say, I'm concerned that machine learning is not learning anything sensible. And yet, by 2018, realize, oh, wait, there's a weakly supervised version that starts with an assumption, assumes that these categories exist, then one can use machine learning to operationally define them. And then I think what we've seen over the past few years in revisiting the strong force is that my subfield of jet physics has kind of crossed an important threshold where machine learning is now yielding insights that go beyond traditional analysis techniques. And I'm learning things that I never imagined that I would have learned 5 years ago. And as director of this Institute for Artificial Intelligence and Fundamental Interactions, I'd be happy if some other folks in this room might be interested in joining this ride. Thanks very much.
questions?
Just very nice talk. Thank you. I have a question about the Colloquium classification.
Yeah.
So you show these nice pictures where you have two types of beans in the jelly jar. And what happens if you have a third type of bean, which you don't have any fluid amount? So speaking in the jet language, and then your sample has some emergent jets.
Yep.
Which either works or fluids.
Yep.
How does it work in this case?
Good. So let's say there's a third category in there. What happens? If you only have two mixtures, it will happily give you decision boundaries between two categories, but you don't know what those categories are in terms of the underlying labels. So what you would need is you would need a third category. And if you do that third category, then these folks here, so Scott et al. Or Blanchard, they show you how you actually deal with that case of having three categories and how you separate them out. And in talking with them, they said, this is in principle, it works. In practice, they find that it's quite subtle and very sensitive to statistical fluctuations. So we have been able to successfully extract up-type quarks, down-type quarks, and gluons from a sample of Z plus jet, dijet, and gamma plus jet in simulation, not in real data. And I think it's well, let me say this. I know how to quantify the problem. So if you give me a third sample, I can tell you to what extent that third sample is not a good mixture of the other two. So I can quantify that there's an issue. But in terms of actually finding a solution, I would say that this is an open area for investigation where even the computer scientists are concerned about whether their techniques are robust. So I think that partially answers your question, that if there were a third category and you had a third sample, you could check the assumption. But in terms of actually extracting that third category, we've only been able to successfully do it on simulation. And when we try to approach it with data, we see some of these statistical challenges that our statistician friends.
Presumably, if you know that there's exactly three categories, just linear algebra, you have
Yes.
three samples,
Yes.
so you can extract it.
Yes.
Now, what if you don't know what other color beings there are?
Good. So what you do is you do 2, 3, 4, 5, 6, and then you end up determining kind of the rank of the rank of the structure. Of course, numerically, you're always, if you ask for 6 categories, you're always going to get 6 categories. But you'll see that the fraction of that 6th category is very, very small. So part of what we were trying to do, in this thing that I didn't show, which I skipped over, and why it took so long for us to actually succeed, is that for those of you who know, these are called rock curves. These tell you how much separation power that you have. Diagonal means no separation power. And if someone sees this rock curve here, like just barely deflecting, like you're saying, whoa, you were able to do this analysis with that barely deflecting separation power? And this was, so I forget how many jets, like millions of jets to do this. And you can even start to see like the statistical uncertainties. It's like, it is really challenging to do. So you need monstrous data sets. And then what we actually developed was a technique that instead of doing what I showed you in the equations, we actually found a fun extrapolation technique that tries to extrapolate the slopes of the rock curves at the endpoints. That turns out to be a bit more robust, but still not quite robust to be able to disentangle at the level that you would ideally want to do. But I would say we're making steps towards being able to robustly say whether something is better modeled by n versus n plus 1 categories.
Right. Maybe just a quick, more
Yeah.
technical question.
Yeah.
So when you do this separation using the forward versus center,
Yes.
this is just one possible mixture.
Correct.
Have you tried anything different?
In fact, what you could try to do is say, let me find the optimal way of dividing things in order to get the best separation power. The problem, there aren't actually that many phase space variables that you can use, and unfortunately, as you change in scale, a lot of things that you'd want to do actually break this assumption of perfect mixtures.
Right, but what if you use just physics processes, say W plus J
Yep.
versus UCD?
As I said, we did Z plus jet, gamma plus jet, which are very similar, but enough to get a separation, plus dijet, you can do it. Yeah. So yeah, different physics processes are one way to do it, but you have to look at jets at the same PT, otherwise you violate the assumption of mixing. Which oh yeah, absolutely. Yes. Yeah.
First of all, what was the second? What is mass?
Well, so mass is the coloring, which is kind of going on this diagonal. So mass is, it's at a funny slope, but mass is basically a linear combination of energy sharing and opening angle. And then it separates out those two coordinates separately. So this is like the collinear degrees of freedom going this way and the soft degrees of freedom going this way. So mass gives you a 1D shading of this. Well, mass is, I don't know, it's hard to tell. Blue is over here and red's over here, so this is the color scheme. So this thing got spread out, so it's a little bit hard to see what the angle is. Yeah. So for people who don't know about optimal transport, you might say, whatever I said way too quickly on this previous slide about what I was doing, this thing sounds like a very data sciencey thing. Why does this have anything to do? Why is this particular way of triangulating the space or defining notions of distance, why does this have anything to do with then the coordinates that I see end up being the ones that correspond to this ultra Parisi? Like, why should they be mapping? And we didn't have an answer, except for I have an email from my grad student who says, oh yes, I have a proof that particular way of doing optimal transport is the only way of doing this triangulation that preserves a certain property. And so I will read this email tonight and see whether whether I believe it. But I couldn't believe that it picked these coordinates. It could have picked something else. And so the fact that it's getting these ones out. Well, and this geometry that you get here. Yeah. And there's in fact, if I were giving you a longer talk, I could tell you how this geometry actually explains like 3 or 4 of my own papers that I wrote pre my machine learning. I was anti-machine learning because I was doing things with my brain, and then realizing that this language actually makes the equations that I was doing much shorter and easier to understand. And I don't know why. I didn't know why, but maybe my grad student has figured out why. This is the one that uniquely kind of gives you this intuitive structure.
More questions?
No.
Going back to what you said about finding new insights into the nuclear force, that there was this discrepancy between your analysis and what you could get out of simulations.
Yes.
Is it a problem with the simulations themselves, or is there some actual insight into the theory of the strong nuclear force?
Yeah, good. So here I'm showing, so the horizontal line is a first principles calculation. The wiggly solid line, that's with all the uncertainties, that's the experimental thing. And then the simulation is the dashed, and it goes up like the wrong slope. And there are 2 things that are going on here. One is that there actually is a parameter choice in this simulation that has been tuned to one data set, and it's known that tuning to one data set breaks this comparison here. So if this were not a CMS institution, but an Atlas institution, there would be someone in the front row saying, Jesse, you didn't use the A14 Atlas tune. And I say, yes, I know we didn't, and I could try to dance my way around that question. So that's one aspect of it. But that's the uninteresting aspect of it that has to do with how you would choose parameters of your simulation. The more interesting aspect of this is that in the simulation, when there's labels that say, hi, I'm a quark, hi, I'm a gluon, those aren't physical labels. And if you actually go and apply this same technique on the simulation, that is, don't trust the simulation's labels, but just treat the simulation as if it were real data and apply this, then a lot of that discrepancy actually goes away. That is, the discrepancy is a discrepancy of interpretation, where in the simulation you have an ambiguous label that you're trying to assign physical meaning to, but it actually is not physical. And so, there's a benefit to having simulation where you think you know what's going on, but there's also a benefit for thinking about things from a purely data-driven perspective about what actually information can I extract. And if there's some latent variable inside your simulation, you have to be a little bit careful about assigning physical meaning to it if there's no way from the outside in a purely data-driven way to get access to it. That give you some sense of... Yeah.
I think so.
Yeah.
Jesse, but then you tried to say compare it to Hurwig, which has different partial model.
We did not compare to Hurwig. By this point, Serhii graduated. Patrick left the field to work in quantitative finance, and I was exhausted. and that's the Right, that's what the pandemic did for me. It totally wiped out this research direction. So now we have to train a new group of people who can carry on the analysis. Yeah.
Could you tell us a bit about what are the hopes, if any, of finding any new physics in this jets that you study?
In the stuff that I showed here, the chances of finding something new is very, very small. However, these techniques, when combined with other analyses, has enormous discovery potential. And last week I was at Rutgers, where there was a machine learning for jets workshop, ML for jets. And this koala idea that I showed you showed up in like 4 or 5 talks where they're trying to apply this, the concept in data, but doing it in a way that's statistically more robust, so that you could actually might be able to identify a source of new physics if it were to exist, and to assign it a robust p-value for the comparison against the null. And so that was really exciting to see. Again, the proof for this qual is like 2 lines, which of course I'm not showing you, but it just relies on the fact that mixed samples and pure samples are related in this monotonic way. And that's just a generic statement about these equations. Then someone can come in and say, okay, now I want to look for a new phenomena. How do I design my analysis to make it kind of like a 2-category thing in such a way that I can actually robustly say whether something's there or not? And so there's a variety of so this is koala. There's, what were the other acronyms that came up? There was a joke about like people were like trying to one-up each other in terms of acronyms. So there was curtains was one of them. Anode was one. And then there was a more trolly answer, which was cathode. So they're trying to kind of one-up each other in terms of different strategies for looking for new physics using the same statistical idea.
More questions?
Yeah.
This question is less about the physics and more about just how did you kind of initiate and what were the mechanics of the collaboration with other fields? For example, a statistician might not know anything about what a quark or a gluon is.
Right. So for the story that I told you here, this was all happening within the physics world in terms of the collaborations. And so here, this was my grad students convincing me of the value of machine learning and me running with them. Now, we learned about this stuff from other people's papers. So, Scott is someone we interacted with for the stuff on optimal transport. We talked to quantum information scientist Justin Solomon's a computational geometer at MIT, but we didn't collaborate with them. Because from their perspective, like, well, my paper's already out. You're welcome to use my work, but why? But they don't want to collaborate on the project because they're part of it, that their intellectual contribution was already published. What we're doing right now is actually trying to, with IFI, our AI Institute, we're really trying to have two-way exchange, and the extrapolation of the story that I told about this optimal transport turns out to be really interesting from the perspective of computer scientist Demba Ba at Harvard. So these blobs here, as a particle physicist, I love those blobs. Like I see this and this gives me warm, fuzzy feelings, and okay. But most of the time you look at that, you say that's just structureless information, or very lacking in structure. Whereas my colleague Demba, he deals with similar types of data sets that actually have all sorts of fascinating topology and structure to them. And so he's developed a variety of techniques that are trying to do something similar in terms of characterizing these certain patterns. But he didn't think about the challenge that we face in particle physics, that actually of all these dots, a lot of them are just noise. And noise robustness is not something that he had thought that much about. So what we did is we got together and we tried to explain each other's problems, and we didn't succeed. And we kept trying to do it. And then eventually we kind of gave up and said, okay, the grad students should talk to each other. And they actually figured out what was going on. And so the story is the following. In machine learning language, the problem that we're trying to solve now jointly in a paper together, in a collaboration that really is equal weight on both sides, we have a loss function that has 3 terms. The first 2 terms are Demba's terms. The last two terms are my team's terms. What they're gaining from us is this third term, which has an interpretation as being noise robustness. What we're gaining from them is this first term, which adds a certain degree of, so it's something that's called dictionary learning. It basically assigns interesting probabilistic interpretation to our data set that isn't present in what I have here. All these three things together give you a strategy for understanding collider data, which is really powerful, but also he's really excited about it because it gives him a noise-robust way of analyzing the data sets that he cares about. That's been 18 months of dialogue back and forth, trying to understand what we were talking about. I accused Demba of not understanding his own problem, and really it was my own hubris that I didn't understand what he was trying to do. And once we finally realized what we were trying to do together, we realized, oh wait, we were just looking at, as people refer to, like different parts of the elephant. And so we were able to put them all together into a tool that's more powerful than anything you would have gotten from each individual subdomain. But it's a long, challenging process. As you said, he doesn't understand anything about quarks and gluons, but he understands Wasserstein distances, which ends up being the organizing theme behind this joint work.
More questions?
Yeah.
Do you ever see something of this sort of recommendation engine of what experiment to do next ever being a thing? In the sense of like doing the experiment that would be most informative for discriminating between different hypotheses and such?
Well, it's already being used. The question is whether it will ever impact my field, and the challenge there is that you don't actually have that much control from the people who run the accelerators. They love this stuff, and in fact, people who run like fusion reactors, which don't yet exist, but they will. The kind of test beds are using this stuff already. But for our field, we don't get to make decisions about. We end up making very big, monumental decisions that then have impact, long term down the road. So, we get to build one tunnel where we put the LHC in. In fact, in that same tunnel, we had a previous collider LEP, and it was just too expensive to build another tunnel, so you just reuse that same infrastructure. So we don't have the ability to, in a cheap way, change the way that we acquire data. And so there is this optimization, but it's very difficult to do in terms of real time. The place where it may have an impact, where this kind of real-time decision-making may have an impact, is in a part of the collider data analysis process that's called triggering. So you're colliding every 25 nanoseconds. You actually can't store all that to tape. So you have to decide, what one do I want to keep, what one do I not want to keep, do I want to store in high resolution or low resolution? And so it may be that some type of active learning or reinforcement learning could be helpful in that domain. But that makes people really scared, because they would like to know, what is their detector going to do, or what is their data acquisition software going to do, and not have it change over time as the machine is kind of deciding to do some type of exploration. But maybe that will be how it shows up. But in smaller scale things, or especially cases where you can do real-time control, like LIGO is looking at this for how to control their gravitational wave observations, about having like real-time decisions about how you tune knobs, and it hasn't gotten there yet, but it may.
Okay, if there are no more questions, let's thank Jesse again for the beautiful talk.
All right, thank you.